I think we will have more coffee, but probably not until 1:30, right?
Yep. We'll do.
Okay.
Well, probably later.
Probably later.
Forget every single day.
Yeah. And a little.
In fact, I'm gonna go down now.
Okay.
What's that? That's good. Yeah, thanks. Yes, we can start then.
Yeah. Okay.
Okay. So we'll jump back into this. Just kind of as a reminder, before lunch, we're doing the state vector class. We saw that you can use the state vector commands like make a state vector object. Have that .add command where we said, hey, we're going to be designing these variables. They have some names. And this is the data catalog that they're located in. And then we started designing dimensions a little, and I was kind of doing this end trend example where we, I think when I was typing it earlier, we did the northern hemisphere, but here I've just copied the code from the demo where I think it's like the extra tropical northern hemisphere, so north of 35. And we said that time was our ensemble dimension, and that we're going to use January as a reference point for possible ensemble numbers. So I'm just going to kind of reset everything here. You remember, we kind of look at our state vector, see, okay, cool. It's not that enormous, ridiculous length that we saw before. This is because one, the latitude dimension is a lot shorter because we restricted it to the extratropical part of the northern hemisphere, and also that time into an ensemble dimension. So the next thing we're going to do is we're going to implement any sequences we might have. So you can do this using the sequence command. Excuse me. So the just should I have a mic for the Zoom, or it doesn't look like anyone does it.
Well, that mic's on right there, right?
Yeah,
So you're
behind you.
so it behind you.
Oh. Okay, cool.
Yeah.
Cool.
No, it's on right now, but it is recording, so.
Okay, great. Got it. Yeah. So a lot of these commands in state vector toolbox or class, they kind of start off with the first thing is you list the variables that you want to design, and then you list the dimensions that you want to design. So these first two inputs are very similar to the design command. This is what variables do you want to add sequence to, and what ensemble dimension should be given a sequence. Indices, these are going to be those sequence indices that we talked about earlier. As a reminder, those are offsets from the reference points. And then the last thing we'll need some metadata for our sequence. We kind of jumped back to the concepts that we looked at earlier. Recall that when we make a sequence, like, yes, we have this metadata along the columns, like we do with all ensemble dimensions, but there's also going to be some structure down the state vector itself. So when you call the sequence command, you need to create some metadata that's going to be associated with those like offset indices. As before, metadata is really flexible, kind of use what you like, but it should have one row per like offset index. Here. Yeah, so I guess we'll just kind of jump right back into the console here. So here's my console. Let's do this in a series. So in this end trend example, we have the summer temperature field, that was our T variable. We're going to add in like a global mean index. In fact, I think I called this TJJA. Oops, TJJA in the morning. And we're also going to add in like the monthly field for each. The spatial field for each month. And so that's the variable that's going to be getting our sequence. You know, we want to have the January field, we have the February field, the March field. So we're going to need to add in a sequence that's going to select each month from that reference point of January. So our indices are going to be 0 through 11. The 0 index is going to be selecting January. Since January is the reference point, we don't need to offset at all to the right of January. And you know, February would be the +1, March would be the +2, etc. The other thing we're going to do is we need some metadata for our sequence. And maybe I'll call this sequence metadata so it doesn't overwrite our other metadata here. And I'm going to use like the name of each of the different months. And I'm just going to copy it from the demo code so you don't have to watch me type it out here. Yeah, but so, you know, if we create this variable, look at our sequence metadata, we can see that it has, you know, it's all these month names and it has one row for index that we're using the sequence. So now go ahead and let's try to scroll this up. So now we'll do our sequence command. SV is SV.sequence. I'm going to say, all right, we're going to be editing T monthly variable. And the sequence is going along the time dimension. We have our indices made right here. Let's call them sequence indices, just in case we use any other indices later. And then here's our sequence metadata. We're saying, all right, that 0 offset, that's the month of January. That 1 offset, that's February. So now if we run this, we can we can look at the state vector. We see, this T monthly variable, like it's quite a bit bigger now. This is because now it's a spatial grid, but it's also a spatial grid over 12 different points in time. So there's our sequence. Anyone have questions on that? All right. So the next thing we're going to do is we want to take a mean of everything. And so in this example, I'm going to be taking 2 means. One, that JJA variable, we want to take a mean over the summer months. But separately, that temperature index variable, we're going to take a mean over like the summer months over the spatial field itself. Excuse me. So there's 2 kind of commands that you can use for doing means within a state vector. There's mean and weighted mean, which do what they say, what they suggest. So to use the mean command, again, our syntax is going to start off with the variables that we're giving a mean and the dimensions that we're taking a mean over. There's also optionally a third input that we'll use when we take a mean over an ensemble dimension. So if you take a mean over a state dimension, like let's say I want to take a mean over every latitude point. I don't need any indices because that's kind of already organized down the state vector itself. So we can just select out every latitude point and take a mean there. And there's no real problem. As we talked about earlier, though, when we do an ensemble dimension like time, we want to take a time mean. Time is mostly organized along the columns of the state vector. So we need to use those mean indices. We'll use these mean indices that we talked about earlier to indicate, you know, which points we should be using for a time mean. So, yeah, if your dimension here is an ensemble dimension, then you are also required to. This thing I broke the hyperlink. You're going to be required to give it some mean indices. And again, as with the sequence indices, Those are just going to be offsets from the for the weighted mean command, it's a fairly similar syntax, except you're going to indicate the weights as the third input. So if you're taking a weighted mean over a state dimension, you just provide the weights directly. If you're taking a weighted mean over an ensemble dimension, so for example, maybe you're selecting the dryer from different climate models, and you think like some of the models are very similar, so we want to give them like different weights. If you want to do that, you should first use the mean command to indicate the mean indices, and then you use the weighted mean command. So kind of for how this would look then, go back to this example. I want the temperature variable to use a, actually I want both the temperature and the temperature index variable to implement a temporal mean over June, July, and August. So indices for this are going to be January is our 0 point. So June, July, and August would be 7 through 9, right? May, June, January 0, yeah. No, it's 5 through 5 through 7. Yeah. The offsets can be a little tricky when you're working with months because like my brain thinks that 5 is May, but you have to remember that it's offset from January or whatever. So 5 in this case would be June. I suppose you can make February your reference point. No, you make December of the year before. Yeah, okay. Think about offsets here. There we go. So I'm going to do speed with speed on mean. We're going to be doing a mean over the TJJA variable. And I just realized, I think I typed it in as T earlier instead of TJJA, so I'm just going to rerun my code so that that's correct. I updated the variable name here. There we go. Yeah, okay, so we're going to do the TJJA variable. We're going to do the T index variable. Both of them are going to be getting a temporal mean. We're taking this mean over the time dimension, and time is an ensemble dimension, so we're going to give it these indices. In fact, let's call these indices JJA. I think that would be a little more clear. So now if we run this code, we can see, actually, I guess we don't really see any difference, but a mean has been applied. If you go into the show details for these variables, to show all details, you can see that yeah, here it is. We're taking mean over the time dimension and we're using mean indices. So the other thing we wanted to do is we wanted to do spatial mean. And we should actually do a weighted spatial mean because in this climate model output, the size of the climate model grid cells are going to get smaller as we move up to higher latitudes. So the weights that we want to use, we're applying these weights to the latitude dimension. Over longitude, like along the longitude dimension, the grid points at a specific longitude are not going to change in area. So we only need the weighted mean for the latitudes. So the way this might look is, first we want to take a mean over longitude for that spatial temperature index variable. We're taking this mean over longitude, and longitude is a state dimension, so that's it. We don't have to do anything else there. But we want to do these latitude weights. And if you remember, we have these indices for our that point to the extratropical latitude metadata. So let's go ahead and pull our latitudes out of the metadata. Here I'm indexing in the latitude metadata, and I'm saying, hey, give me those extratropical values. And then we're going to take the cosine of those latitudes. Cos D means we're doing cosine in degrees, because our latitudes are in degrees. If you just use MATLAB's like COS cos function, that will be in radians. That would be incorrect here. So now we'll do a weighted mean. Again, this is applied to the index variable. And this is the latitude dimension. And here are the weights. So if we run all this code. Weighted mean. That. Okay, clearing the console. If we look at our updated objects, we can now see that this index variable is a single data element long, and that is the longitude mean and also the latitude mean. And again, you could go into details and also see that latitude is a weighted. So,
Yeah, can you show it? Because I'm struggling. I have to figure out where it shows it's weighted.
oh, maybe it doesn't. I could be wrong.
I mean, I could be wrong.
No, oh, I looked at that. Let's see. Oh yeah, this should say weighted. Okay. Write it notes myself.
That's in the details.
Yeah.
Does it show all of them? Is that
I notes myself and fix that.
all?
I promise you though that the it really is implementing a weighted mean. Those weights really are in there. That's just the console printer. One thing about these mean commands is you can also you can combine multiple dimensions into like one call. So you see here we have sv.mean where we did it over the time dimension. We did sv.mean where we did it over the longitude dimension. We can actually just group those together into the same command.
Jonathan, can you show again where that detailed information
Yeah.
is? Sorry.
So like when you have the state vector display,
Yeah,
you get these show details links for
Yeah.
each variable.
yeah.
So we'll look at this one. This will kind of give you a brief summary of the variable. You can look at more details, mostly just stuff about coupling.
Right.
You can also look at the individual dimensions. So
Right.
here we're seeing time as an ensemble dimension. It's got 1156 reference indices. It's implementing a mean, but this should say weighted. And yeah, you can look at even more details to see like there's no sequence for this variable and some stuff about metadata that we
I
would
see.
worry about.
Okay. Gotcha.
Yeah, and you have your June, July, August. Too. Like
Yes.
6, 7 there.
Michelle, back to your previous question about days and months. I mean, I think that NCAR output is always 30 days a month anyway. right?
Okay.
I think so, yeah.
So it really depends on whether your model is, I mean, the model, if you're getting monthly data out of the model, it should already be like, should be there a month, but it might be a different month depending on.
Right, that
I
makes
think
sense.
NCAR has 30.
At least
Okay.
has 30 days.
Really? Okay. So then would you want to weight it at all? I mean, it's.
Never have, but
Yeah.
you could.
You don't think most people do. Like,
Yeah.
it's fun.
Is there anything adjustment in Dash, or do you need to do that before?
It would be your calendar adjustment when you define what the metadata is.
Yeah,
Say like calendar for like orbital, that needs to be done.
I
Like,
want you
to the actual output
okay, yeah,
separately, yeah. So you should do any calendar adjustments before you do the batch. We don't have that till like that.
I'm gonna back up here to when we like combine multiple dimensions here. If both of these were state dimensions, you know, the command might just look like this because state dimensions don't get mean indices. But if at least one of the dimensions has mean indices, then you should group the indices for the dimensions in the cell. Now, this raises the question, what do I do if I have a state dimension and an ensemble dimension? Because state dimensions don't have mean indices. So if you have a state dimension, you can just give it an empty array as just an empty placeholder. So this is kind of what the groups command look like, where I'm going to implement a mean over these variables and implement means over the longitude and the time dimensions. Longitude is a state dimension, so we don't have to worry about indices. And for time, we're taking a mean over JJA. And then we could, yeah, I guess we could delete this command out here if we wanted to. Yeah, so it's taking a mean. I think, yeah, we ran the code. Yeah, any more questions there?
Okay.
Yeah.
Not sure what is T.
Here I'm saying it's a like a I guess it wouldn't be a global index, but it would be the mean spatial.
Okay.
Yeah,
Like a time series of extra trackable.
extra trackable temperature.
That's a time series.
So you might do that if you wanted to put global mean surface temperature in your state vector, for example.
Yeah, if you
do
wanted to,
that,
like,
hopefully you would have, it would be a global rather than just extra tropical.
This one here, because when we use the design command, we requested latitude elements from the extratropical region. So this one here would actually be an extratropical. It wouldn't be a global mean.
Yes, yeah.
Yeah.
Yeah, this isn't global mean, but it's just JJA extratropical mean, so just one time series. You don't have to, I mean, you can put that, when that might be useful is like, if that's what you're really interested in reconstructing. You know, it might make sense to set it up this way, because later it'll make your assimilation really fast. If you still want the whole field from your assimilation, you can always calculate these means afterwards, you know. So this is just like, yeah, let's say you're like, I just want to do a DA and get a time series out.
Yeah, I don't care about spatial.
I don't care about spatial anything, you can put it like this. But you don't have to, you know, it's calculate it after. Yeah, if that's all you want to reconstruct, because later then you can just use that.
You can think about like if you reconstructed this June, July, August spatial field, you know, you have to update 4,320, you know, data points, whereas if you just do the index, you only have to update. So it's 1,000 times faster. So I think, yeah, so, okay, so at this point, we're gonna take a look at our state vector here. This is kind of our final state vector. We're ready to actually build something. And so the way you build is using the build command. And the output, or kind of the syntax for command is you'll get some output. No, we'll start with the inputs. The first input is like the number of ensemble members that you want to build. Alternatively, you can put in the string all, and Dash will build every ensemble member that it thinks is valid. We mentioned earlier that like if a sequence or if a mean like fell outside of or like extended outside of your data catalog, that would not be a valid ensemble member, and Dash would not try to build that. You'll get some outputs when you do this. You'll get X, which is our actual state vector ensemble. It's a big data matrix. And you also get this ensemble metadata object, which we'll kind of talk a bit more about as we go. But I think Ronnie, you asked about this earlier. This ensemble metadata object is what like keeps track of what and where things are in the state vector, so that you can locate specific data or regrid variables out of it later. So yeah, let's just go ahead and run this right now. Just as an example. Let's build, we'll just do like a little small ensemble here. So we're gonna build 10 ensemble members. And it's gonna go, it's gonna think, okay, it finished building. So we look over here in our workspace, we can see that X variable, that is the model prior, essentially. You can see it has one row for each like state vector element. This is the 56,000 something rows that we saw we had earlier. And we can see that it has 10 columns here. I'll put it in the console too. Is this font big enough? I feel like it maybe got some.
I don't think you ever increase the command
Okay.
window size, and I just figured out how to do it to just send my own, so you just go up to MATLAB to preferences,
Okay.
it's pretty straightforward.
Let's see.
So font. And then you can move it up to like.
Oh, nice.
14 or something.
Yeah, let's see that.
And you might have to undo.
No, that's too. No, that's big.
Actually, it's across the back,
Yeah.
but 12 might be okay.
Let's try 12 because I might die. Okay, I'm okay with that. Is that?
Yeah,
doable?
that's better, I think, yeah.
Okay.
You might have to zoom out when you get back to the editor, 'cause it might be 12 zoomed in now.
That looks pretty good. Yeah, so that's our data matrix. We also have, so in good console, we also have that ensemble metadata object. And we can see that like, we're not gonna go into this just yet, but it's keeping track of like, okay, this is the first 4,320 rows, that's this variable, it's got this longitude, this latitude metadata. The next row is the index variable, and following that is the monthly variable, which is longitude and latitude, and it knows what the different, months in the time sequence are. We'll come back more to this later, but just know that that's enough. Now, if you run the build command just like default like this, it's going to sample the reference indices just at random. You're just going to be building a random ensemble. But sometimes it can be useful to build your prior like ordered in time. If it came up in the workshop, maybe you might have a forward model that actually has some memory in it. And so you want your ensemble members to be ordered. Or, I mean, for other times, it's just useful to have it ordered if you think you might want to go and like look at specific points in time later. So if you want to do this, you're going to order it in time. You can add in this sequential flag, sequential, and then indicates true. I want you to build in this sequential fashion.
So is it gonna build the first 10 possibilities or 10 random and then make them sequential?
It's going to choose the first 10. So here, I'll back up a second. That ensemble metadata object that we had earlier, it's describing our, like this X matrix right here, right? So let's see what happens. There's a command in there where you can look at like what the metadata is across different columns. So I'll do onsmeta.columns. I'll say, I want to know the metadata across the time dimension for those columns. Maybe it's not called that. It's called members. Okay, onsmeta.members. Time. We can see these were the ensemble members that went into this ensemble down here that we built. It's a bunch of random years, right? So now let's rebuild this again. So we're going to do X sequential, meta sequential. It's going to be SV, and we can use that same state vector object that we had earlier to build again. It's just a design template. There's no data associated with it. So now we're going to build a 10-member ensemble, but going to make it sequential. Done. So here's the ensemble metadata for that new one. And if we look at the ensemble member metadata there, you can see it's 850.
So if you do the default setting, it's randomly
Different.
and if you run it again, it would different random.
You get different years.
And I'm assuming not that you have to go into it, but there'd be a way to like pick the middle 10 years or like not a safe.
Yeah. So that's probably something you do back when we did the design process.
Right.
Instead of saying January of any year, you'd say, give me Januaries of these specific years. So if I wanted to modify the code up here, you could do something like, here's January, and you could do like pre-industrial is when the year is less than 1850. And then you would do down here like pi, pre-industrial and January.
So it has to be like a C random.
Yeah, so MATLAB has a function called RNG. Yeah, which you can use to see the random number generator. I think the input I use here the most is just to do default. That'll set it to some C that's the same across like everybody's MATLAB release. And so that's nice if you want to do like reproducible demos using random.
Sequential is also a good way to sort of do a little sanity check, right? Like,
Yeah,
like create an ensemble with all the January temperatures and then, you know, go into your data, just the old fashioned way, pull out the January temperature.
make sure.
That was the first thing I did. It's like, all right, this is super powerful. I want to make sure it's doing what it is. So, yeah. So sequential is a nice way to sort of check.
Yeah, if you're gonna use all the possible ensemble members anyway,
Might as
you
well
might as
just
well
use
make it sequential so that you have some sort of order.
Okay. So there's another option in here for the build command. And that is that we can save our ensemble to an ensemble file. We're going to talk a lot more about those kind of over the next few sections. But essentially, you know, this is going to do, if you have a really, really big state vector, Dan, we were talking about this a little bit at lunch. Like sometimes that state vector might be so big that you can't really fit it all in memory, especially when it's over an ensemble. But if you save everything to file, Dash has a bunch of optimizations, so it doesn't necessarily have to load everything to memory if it thinks it's too large. Also, by saving in file, I mentioned kind of in the overview of Dash at the beginning of the day that we have the ensemble class, and that gives you tools to manipulate like ensembles that are stored in these files. In general, I would honestly recommend just always saving the file. I find it really useful if I'm working and then go get lunch and come back and I don't want to have to like regenerate the ensemble. Like the ensemble is saved, it's right there, just pick it up and start working with it again. If you were working with random draws too, and you came back after lunch, you might, accidentally draw a different prior, which might not matter. So the way you're going to do this is by using the file flag. The way this would look is I would go SV build. Let's build a big one here. Let's just build it with everything. And we'll build it sequential. True. And then we're going to use this file flag, and the following input is going to be like the name of the file that we want it to be. So I'm going to create entrend.ens or .ons for ensemble. When you save things into an ensemble file, they're always going to have this .ens extension. If you don't include it in the file name, Dash will just add it in automatically. Yeah. I should note that apart from the first input, all of these others are just kind of optional flags. You can provide, like, you can do file, you don't have to say anything about sequential, you can do this in a different order. It's just like flag value, flag value. So if I were to do this, it's gonna be like, okay, you want to build all of them? That's gonna be that many ensemble members. If you look over here, you can see I have entrend.ons. Right now, it's a temporary file. That's what that .tmp extension is. But once you finish building, there's our ensemble file. We'll talk more about this kind of as we go through the next sections too, but Dash gives you this ensemble command. This is very similar to like the grid file command, where we wanted to look at the data catalog in the file. The ensemble command lets us look at the ensemble that's in the file. So here the input is the name of the ensemble file. I'll just call this like this. You see, okay, that's what's in that file. There's static ensemble, it's got its variables, it's got length. Yeah. They have jumped slightly. I'm kind of working on a different page, so we'll just go ahead. And talk about just one or two commands that we care about here with this ensemble class. There's a lot of commands in the ensemble class. We're not going to talk about most of them today. One of the ones I want to highlight is that you can use this class to build an evolving ensemble. And that's something that just probably is for, I think, a lot of the deep time folks. So, yeah. Yeah, so the ensemble command lets you look at the data in the file. It's great. And we just did that. The other thing that it can do is it can return that ensemble metadata object that we looked at earlier. And so the command to do this is ensemble.metadata. So let's just like clear everything. I still have my ensemble that I built up here. My state vector is gone now, but it's fine. I built the ensemble. I don't need it. So here we'll make our ensemble object. We say, hey, what's in that entrend.object? Okay, cool. There's the ensemble object. And we can get some ensemble metadata by doing metadata. Also update this down here so we kind of have this on record. So build sequentially, right to this file. As with grid file, you can tell statevector.build that you wanted to overwrite an existing file. You can use the overwrite flag, true. If you're playing around and generating multiple different files. Otherwise, like if I try to run this command again, it's going to get unhappy because it's like that already exists. Oops, right. I think you. Okay. Yeah. Blah, blah, blah. It's like, nope, that file's already there. But, yeah, if you use that overwrite flag, that will allow you to rewrite. Okay, so I'm going to clear it and do again. Let's start a new script here. So now we're working with ensembles a little bit. Let's get ensemble. This is the command we were looking at. Ensemble entrend. Once. And then we want to get ensemble metadata. So if you evaluate that, let's run this. Yeah, you can see here's our metadata object. Before I was showing the members command to look at the data in different ensemble members. So look at ensemble. That would be meta members. And you should indicate what dimension you care about. So I want to look at the metadata from the time dimension. If we did that for this one, you'll remember we built the state vector using everything and we built sequentially. So we should be seeing the Januaries from 850 to 2005. Is back to get. I'm not going to scroll to its 850. There's a lot of commands in the ensemble metadata class. Also, it's a real utility class. You can use it to check, what metadata is along rows of the state vector. We're not going to go into it in super huge detail today, but maybe I'll just toss in a command here to show like, here, what's the rows? What's the metadata down the rows? Maybe for the time dimension. We should see those months of the year that we put in that sequence. See, there's our December spatial field. Scroll up a ways, we'll eventually be like, okay, a lot of rows of December. Okay, eventually we get up to rows of November. And you can use this to index variables. You can, query the latitude metadata to figure out what's near your proxy site or the longitude. So. Okay. Does anyone have any questions about like the ensemble and just kind of metadata?
One quick question.
Yeah.
So when everything has to be in the same folder. can I have like a separate folders for NC files and then have
Oh, yeah, yeah.
the grid files in separate?
Yeah, the main thing is the grid file records the path to the the data source files, the netcdf files. It usually does it as a relative path. So like, I can pick up these files here. Where's the grid file? Here it is. And if I move these, like right now, this grid file knows that these two files should be in the same folder as it. So I can move these anywhere on my computer and it'll, as long as they're in the same folder, they're good. There's also a an option when you're building a grid file catalog where if you want to give it an absolute path, you could say the path is like always here. Or you can give it like an open URL for anyone who uses that and be like, oh, cool. Don't look in a folder, like go to this open URL or whatever that absolute path is. And then you can move the grid file around too.
Like for ocean Atlas data.
Yeah.
Is that what's happening in the LGM folder? There's no.
These are the netcdfs. They just have a really long file.
For the entrance. But I'm saying for the LGM.
Oh, part of the LGM is just like we did a bunch of collecting different model things and time averaging them into climatologies and whatnot. I didn't want people to have to worry about that data today just for time. So I just went ahead and I saved it all into a mat file, and that's why it's there like that. Okay, so that's, the main two commands you need to know there are ensemble creates your ensemble object, ensemble.metadata returns the metadata. Okay, so with this, we can start moving into the forward ones. We're done building state vectors, done building ensembles. It's kind of our next big cool thing. And so the way we're going to do this is using this PSM package, which I've been told is not shouldn't be the name when you use a linear forward model, but I don't care. Yeah. So ultimately, what we need to do is, if you recall, we have this ensemble here. It's got a whole bunch of rows. It's got a whole bunch of members. I'll even load it into the workspace here, so we can just look at it and play around with it. Might take a second. Yeah. But what we need to do is take a proxy system model or a collection of proxy system models, one for each of our proxy records, and we need to generate some proxy estimates. And so the PSM class is going to allow us to do that. The way that the package works is kind of under the hood. It creates an interface that lets you create a wrapper to an external proxy system modeling code. So for example, Prism or the forward models in Jess's Baywatch suite, there's kind of wrapper functions that we've built and put in here. To call those external forward models. I think an important point is that actually writing and running a forward model is that's outside of the scope of Dash. Dash is about doing the data assimilation. And a lot of times these forward model codes kind of live in other places on GitHub. So it's very built around running an external code on these ensembles and state vectors that we built in. Also note that we're going to get into the details of this PSM interface in a bit, but this interface is strictly meant to be as a convenience to you. If you want to run a new forward model and that's not currently supported by Dash, you don't have to use this interface. You can use that ensemble metadata class to find inputs to your forward model. You can run it on your own and you can build your estimates and you'll still be fine when you get to the Kalman filter later. Yeah, so these are the models that are currently supported in Dash. We have kind of the whole Baywatch suite. There's a general this should say multivariate, not multivariance. General multivariate linear model. There's a Palm drug severity index estimator that wrappers to some of the Prism sensor modules, and also the VS Lite tree ring with model. I will caveat that Prism is written in Python, and so there's a little extra setup to get MATLAB to run Python commands. We absolutely do not have time to talk about that today, but if you're interested in that, get in touch, and I can help. I will also comment that MATLAB can be obtained, like if you're used to working in Python and having like different environments or maybe a couple different versions of Python running, MATLAB does not handle that well. So that can be a good time where you just like use the ensemble metadata to pull out like the inputs to Prism, run it separately in Python, pass it back in, outside of this interface. And again, that's perfect. Yeah, so kind of the standard workflow that we'll have here is, the first thing you need to do is just download forward model code. These are, like I said, these are usually external codes, so you can get them on your computer. And so there's this PSM download command that you can use to download those codes. Usually the next thing that you'll do is you're going to create a PSM object for each forward model for each proxy record. We'll get into the details of that in a second. The next thing you'll do is you'll use the ensemble metadata class to like look through the state vector ensemble, be like, oh, here's where the inputs of the forward model are located. And then the last thing is to use this psm.estimate command that will run the forward models on the ensemble using the inputs that are appropriate.
Wait, sorry, is this documents in MATLAB, or are you talking about how you would run this off?
I'm strictly talking about how you can run this within Dash, within the PSM inputs. Really, the only thing that would be different here is if you're doing Python, is you would like, you don't need to bother creating a PSM object because that's a Dash. You download it from PSM. So the main thing you would do is you would take your ensemble metadata class and you'd be like, hey, where is the input? Where are the sea surface temperatures that are closest to this proxy record site? And it'll be like, it's these rows. Pull them out on your own, pass them to Python, let Python do this thing, and then bring those proxy estimates back when you run it all. Is that?
Yeah, I guess it's saying the PSM estimate was run a collection of forward models.
Yes, and I should clarify. Run a collection of like the forward model objects, these PSM objects that are in the Dash toolbox.
Oh, okay.
Yeah, the whole thing that the PSM objects do is they're wrappers to the external code. So when you call PSM.estimate, you're like, here's a bunch of forward model objects, and it goes through each one. It's like, call the external code, give it these inputs. But if you're just running in Python, you won't need the wrapper.
This version 4, the current version we're running support the PSI. Yeah. I just tried PSM download PSI.
Oh, it might not be.
Yeah.
Okay, wait, another note to myself.
Okay, I also had a question that seems kind of relevant, but maybe we'll talk about it later, about just getting proxies on here, because they're like what is the format like that you try?
Yeah, that's a great question. So usually what I've been doing is I put the proxies in the data catalog. So we'll go back to like this ntrend example, like here's the proxy data set, it's in this ntrend.grid. We're just gonna clean up the workspace real quick. So I would do like grid file ntrend. Here's like the proxy data set. We've got our 54 proxy sites over these various time steps. And then I would do the grid file.load command, which we'll also talk about when we actually get to the Kalman filter. But the way that would look would be like y equals, I guess I called it dot load. Let me read it. No, let's call it proxies. Y equals proxies. Our proxy records. Bunch of missing values towards the end, which is pulled out. But if you actually look at the data matrix, you see it's 54 sites by the 1262 times.
Thanks. Is it just like a matter of like adding like a new column or something? If you want to add like new proxy or something?
You want to add new proxies like to an existing data catalog? You'd probably call the grid file.add command again. Add that new file. I will maybe just a brief comment on grid file.load. One thing you can do is you can request like and request things in different dimension orders, so. Right here, I read it out as site by time, if you want instead, we can do time by site. Or I could do, you can also like request specific subsets, so. You know, maybe I want just the first 5 proxies. You see, you know, what was loaded out is now just like it's 5 proxies over time, so. Part of the point of the grid file catalog is to give you the option to like reshape and load your data out in like kind of whatever arrangement you like without needing to actually touch the data yourself.
Are there preloaded like pages 2K or something like that, grid files, and then also like, yeah, if we want to add like a new repository, are there tools to do that from like an Excel spreadsheet or something like that?
From an Excel spreadsheet, I don't have support for Excel yet. I do have support for like delimited text files, like CSV file, if you find.
Like the text files.
No, I mean, I think it's kind of up to you to get your proxy data into a grid file a little bit. I mean, because if you don't know, we don't know the original format of that. I mean, there are some formatted, like you pointed out, it's okay, but that's kind of up to you. So in this case, Jonathan already did the work of putting the tree rings together into a grid file.
But I mean-
like in our case for the LGMR, we have CSV files, we had a NetCDF proxy repository for LGMR that we can call and format into that. But yeah, because there's no universal way that these things.
Yeah,
Yeah.
it's,
Yeah,
But
yeah.
it's like if you built out, you could have, I don't have one built for like pages 2K. But you kind of go through the grid file documentation, there's commands that let you expand the size of a grid file. So if you're like, I made this data catalog for pages 2K, and now I have some new tree ring records, you can like update the catalog itself to add in those new records.
So wait, there's not interesting things.
So I don't have any like pre-existing. Yeah, we could maybe generate one at some point, but for now, I think the point is like for people who did it, so I haven't.
So I guess we should innovate and feed records.
Oh, yes,
So
yeah.
we'll think like I make a pages 2K.
Oh, please, that would be so great.
I know Nick has written contract facilities for reading. the files.
Okay.
So you.
Okay, that'd be great, 'cause it's just so hard to process.
Yeah. They're not this would be-
I mean, yeah, and I want just to add that, like, this is, just from the perspective of proxy generator, like, I sort of philosophically want to make it a little bit hard for people to.
I kind of
get
want you to
into it,
have to think.
Because I don't want the people to just put the kitchen sink into reconstruction as they've done in the past, like, so while these synthesis projects make it easy to do so, doesn't mean you should, so like, like there's a part of me that likes to keep it just slightly the difficulty you actually have to go work as a data generator. Yeah. So, that's my cranky data generator branch.
But this is, I mean, this is basically like, yeah, you have to think about the. It's for long.
you don't have to, like, because I don't, my proxy data are I never
Yeah,
read them, I just have them in a single CSV. I read that in offline separately, and when I enter my data into the common filter, I draw my Y from a variable in MATLAB that I've never put into a grid file, so like that's just, it's an extra step to have data in file. But if you just have like, I don't know how pages handle the data, but if you have like a pages file, you wouldn't even need to.
This kind of also brings up a point. I said that this PSM interface, like, it's strictly for your convenience. Everything we've talked about before is your convenience, with the exception of the actual like Kalman filter algorithm class. You can do all of this stuff on your own and bring it in as your own input. It's like you don't have to use this front end, but it makes it nice.
Yeah, I think if you don't use this front end, you run the risk of making a bad mistake and trying to map your YEs,
Yeah.
and things like that. So that's-
Locating my inputs.
Yeah, exactly. So.
So I think we're gonna, oh, go ahead.
Just one more thing, I guess related to proxies, but like proxy validation, or if you were like going to like manually assign like our values, or like is that like related to like how you have the proxy stored in your own grid file, or I guess maybe just
What I
what
use-
we did, yeah.
There's kind of two ways I get it R. A lot of Jess's Baywatch models, like will estimate R as this running.
Correct.
So sometimes I'll have them calculate that for me. But the other thing I might do is like on my own, I'll like compare some estimates to it, like. I'll like run forward models on like instrumental data sets, and I'll compare those proxy estimates to like the real record. And I'm kind of doing that a little bit outside of that. And it's kind of like some science that I have to do on my own to like get the input that I want for my data. Does that answer?
Yeah.
So like I might just save a variable called R somewhere in a file, and I'll look at it. So I think we're gonna do a little pivot here, and we're gonna switch over to the other demo, because I think it'd be nice to kind of look at using baseline, or one of these external forward model codes. Maybe we'll real quick, we'll just take a quick look at these data set. So we've got a whole bunch of UK 37 records. Looks like we have 89 of them. They're from a single time slice. This is kind of averaged at the average values at the last glacial maximum. That's kind of the point of this demo, is to reconstruct the LGM. Here we can do 837 equals. And if we look at the metadata, yeah, we can look at time slice. So it's from 18,000 years, 18K to 21K. We can look at the proxy characteristics. These are the sites, and these are their latitudes, these are their longitudes. The other thing we could do is look at our climate model data set, which is this SST.grid. You can see there's a whole bunch of information about it. You'll notice something interesting here, which is that it has this really, really long site dimension. And this deserves a comment. This is because the SST data set that we're using here is coming from a tripolar climate model output. And a lot of times, like in the output files, you'll see the grid shaped as like a it'll have like a latitude and a longitude dimension. But the metadata for those dimensions, like it's not fixed. So like if this is like my tripolar model output, like, and this is latitude, these are the longitude points. This latitude point isn't the same as this latitude point, even though they're like in the same row. Like this latitude point isn't the same as the next one either. Like ultimately what we have is a collection of unique spatial points rather than a like rectilinear latitude dimension or longitude dimension. And so when you build the grid file for this, you need to indicate that I'm building from a collection of spatial sites, and that's why things are organized along this site dimension. You can see that there are 12 monthly climatologies here, 12 time steps from January to December. We also have data from 16 different model simulations. Anyone have any questions about that data set?
Have you all seen the tripolar output before? Okay, so we would scan it from MCAR. So the nice thing as well is you do not have to regrid that before using it dash. And go ahead and update the whole tripolar field. And then if you want to regrid it after the fact, just for visualization or something like that, you can do so, but you don't have, Dash doesn't care because it's a state vector, right?
Yeah,
It doesn't matter.
It's just gonna unwrap it into a vector.
Yeah, so all we're doing here is taking the lat long unique points and just, you make a lat long pair, that's a location. So that's the site variable here, the site is actually lat and long together, so. Rather than lat long separate.
So I'm gonna really quick, we're gonna build like the ensemble for this LGM demo here. And just, I'll copy and bring this code over. Like I said, I think this example was a little simpler, so we'll see, this one isn't quite so big as the other example.
If we go back to state vector to find that.
Yeah, so it's the full demo for the LGM back into the state vector code. But what we do here is, we're creating our state vector object. And the variables. We're gonna add in a feed surface temperature variable from this data catalog. So you can see it's got, again, same as before, when we first add the variable, it's ridiculously long because it's known what ensemble dimensions are. Now, in this case, we actually want each of the monthly, we already have the monthly climatologies, and we want the monthly climatologies. So time isn't actually an ensemble dimension here, this is a state dimension. It's sort of gonna automatically implement what you could think of like a sequence for us. We're actually going to select the ensemble members from these 16 different climate model routes. So run is our ensemble dimension. Let's see, okay, it's still long. This is because it's like it's a pretty high resolution model. We got a lot of latitudes, a lot of longitudes. We're gonna. Oh, I'm sorry. We didn't want monthly climatologies. We want the annual mean. So we're gonna take the annual mean here, but time is still a state dimension. So you can see it's getting smaller still because now we've collapsed those 12 months into a single annual mean. And now we're gonna build our state vector ensemble. We're gonna save it into this file here. The models don't really mean anything to me, so I'm not gonna bother to make them sequential. I'm just gonna write everything into this file. Build an ensemble with 16 members. There it is. So call this script LGM. So load ensemble. And actually, no, let's go back to the page. We go back to the PSM page. We're going to start looking at open coding for. So I think I mentioned this back at the top of the day, but we're running just as baseline PSM, which is a forward model for UK 37 values. We're going to run it across this ensemble. If we look, we can take a quick look at the ensemble. We can see like, okay, yeah, we know we have our 16 ensemble members, and we've also got these like 122,000 some spatial points. And what we want to do is we want to locate the SST. So the baseline PSM requires sea surface temperature as an input. And we want to locate the sea surface temperature values from the climate model grid point that's closest to each proxy site. And so that's going to be the crux of kind of what we do in this coding session here. I was talking about the workflow here. First thing that we said we need to do is actually download forward model code. In this case, we want to download baseline. So we have this PSM.download command, and the input it takes is the name of one of the PSMs that Dash supports. You do have to have an internet connection, and you do need to have Git installed on your operating system for this to work. If you don't have that, you can use the, well, here, I'll just show. Okay.
Is it just the case sensitive?
Yeah, okay, so let's just look at PSMs real quick. You can use the psm.info command to like print a bunch of information about the PSMs that are in Dash. And so you can say here, these are like the names that are recognized. And oh yeah, there was Prism is in there, but there were some issues, so I just kind of pulled it up. So this is what's there today. And you can see, like, if you want to download baseline, this is the string Dash uses to recognize baseline. So if you want to do psm.download, do like all lowercase. Yeah. If you don't have Git installed, you can do this psm.github info. That'll tell you like the repository and the commits that the download command is grabbing. you don't remember, I think you can query a specific one if you want. Let's see what happens. Yeah. See, all right, the baseline model, it's on Jess's GitHub. You know, that's the commit hash, and this was the most recent as of a few days ago.
Can I ask you
Yeah.
about the install and get on the system path?
Okay,
Is that, when you say system path, is that different than just?
I just mean on your operating system.
Okay.
Um,
Is there like a really easy way to do that? Tell us one or two lines or should?
I think it's pretty, if you just, honestly, I feel like if you Google git download, it'll pretty much take you there.
Okay,
Um,
cool. I've only ever used it on my Linux workstation.
Oh, gotcha. If you have a Mac, Git is on your machine on the Mac, like
Yeah,
from
I think it's
factory
probably
install.
better, but
Oh, okay,
So you-
because then because I'm getting an error
Mhm.
using the PSM download for baseline.
Okay, it might be a Git thing, yeah, it's usually what it is when that fails, but yeah, just go to GitHub and download it there.
yeah, you can just download, all it's doing is loading it into the folder that you're in, so.
Yeah.
You can just download it and drop it in the folder or your home folder.
And yeah, it doesn't have to be the folder you're in, it just has to be on your MATLAB's active path, so MATLAB knows how to pop it code. Yeah, but so let's say I'm gonna download baseline. Be like, all right, it's the one I want to download. If I run that command. Right, it's Yep. baseline. Okay, it's downloading, cloned it. I can look in this, and here is my forward model. One thing that I'll note is when you run the psm.download command, it's automatically going to add it to MATLAB's active path. So like the code it's immediate and accessible. If you close MATLAB and like start a new MATLAB session, typically MATLAB pulls like just about, it usually resets your path. So you might need to manually go in and add it back to your path. And just as a reminder, you can do this by right clicking like on the folder that you want to add things to. So for example, you see it's kind of grayed out. These commands, like MATLAB doesn't know how to find them now, but I can go to like add the path, select folders, subfolders. Yeah, I can move back there. Okay, so on the PSM objects, these are kind of the key object that we're using for our forward models, and ultimately a PSM object represents the forward model for a specific proxy site. You're going to create one of these by using PSM dot and then the name of the forward model. So PSM.linear creates a linear forward model. PSM.basebar creates a basebar forward model. I'll often call this command the constructor for a given forward model. So you can see that term around. Every forward, the inputs to this constructor command are going to be like parameters for the forward model that are not like climate variables for the ensemble. Every forward model is different, so this is where you really should read the help text and dash documentation, but also like you should know the forward models that you're working with. You should understand them, and you should understand them like outside of the context of dash. But so what we're going to do is we're going to create some baseline objects. And the way I would do this is I would be like, model 1 is equal to PSM.baseline. Now, we should look at the help text. See so it ran. I'll give the answer away. It doesn't require any inputs, but take a look here. You can see we want to create a new baseline object. Default syntax is we don't need any inputs. But by contrast, maybe we wanted to make a linear PSM object. You can see here, okay, if you want to create a linear PSM, you have to provide the linear slopes as like the forward model parameter when you create the object. And so, yeah, just read the documentation for your forward models. That's kind of on you. Baselines are nice though because they don't need any extra parameters. Okay,
I have a question about the.
Yes.
Okay, so is this still, I understand that I have to specify these relationships, but is it still a capital location?
yes,
here?
so that's the next step that we're gonna do, is we're gonna be like, hey, I built this forward model that has these parameters. Dash, when you run this forward model, you need to use this specific like row, the same vector as the input or whatever. That's the next thing.
Is there an easy way to do identity?
Identity observation.
Just like my observation is exactly this. It's just. Your
Oh, like a
observation.
trivial? Huh. I guess I would do it as a linear one with a slope of 1 and intercept of 0, but I can add in a trivial.
So let's use that.
Yeah, totally. What do you prefer as a name? Trivial, null? I like trivial.
I did.
Identity, that's good. Cool. Yeah, so kind of in this demo, we do need to build a different model for each site though, because each site is going to be taking in data from like a different spatial location. I wrote the error. Okay, so we're gonna need to do a for loop here, which I don't think we've talked about yet, but the way that MATLAB does for loops is you do a for, and then like, I don't know, 1 to 5, like whatever you want to loop over. Yeah, I have to write it as a string.
First, you gotta get the site.
That's true. Okay, so we're gonna create a baseline object for each site, and we're gonna loop over all the different sites to do this. But before we do that, we actually need to know what the sites are. So this is a good time to use a grid file to look at the proxy data set and just see how many sites there are. So we'll do get proxy. So we'll do 7. That's the data in this grid file. We'll do sites metadata, K37 site. So if we run that, now we can see the metadata for each site. We see that there's 1 row per site. So number of sites is equal to the size of this site metadata, specifically the number of rows. 1 here is saying like along the first dimension. Cool. So now, if you're using different forward models, they're different objects essentially in Dash. And where I'm going with that is that you'll typically need to group forward models in a cell vector rather than putting them in an array. So we're going to just reallocate cell vector for the models. You can use MATLAB's cell commands to make a cell of a particular size. So the way this would look like would be like models. It's a cell that has the number of sites. And again, MATLAB doesn't have pure vectors, so you have to say with 1 column. Otherwise, it'll make an n site by n site matrix, which is what you want. So if we do this, look at models. Oops. Sites. We can look at our models array. We can see that it's just a big empty cell. There's nothing in it right now, but it's got a spot for each of our 89 forwards. Okay, so next we're going to create model for each proxy site. So we're going to do for 1 to the number of sites. Model is going to be the baseline PSM. And then we're going to store that model in this cell array. So I'm saying, all right, oh, I'm sorry, this should be S equals, I'm sorry, yeah. So for some index, for some variable S, which is going to range from 1 to the number of sites, we're going to create a model, and then we're going to store that in you know, nth spot of this cell vector of points. And we have to end our loop with it. It's a little different from Python. MATLAB doesn't really care about your indenting. So do this. We can look at models now, and we can see that it's filled with all these baseline objects. Again, one baseline for each site. Now let's take a look at a single model here. We'll just look at the very first one. We see that there's this rows input. Currently, this model doesn't have any rows. And so what rows is we need to tell this forward model which rows of the state vector it needs to be inhaling as its inputs. That's kind of our next task here. So the way we'll do this is using the rows command. And effectively what you will pass as the input is the index of the rows that you care about. Let's raise the question, like, how do I actually figure out what the rows that I need are? And so the way we'll do this is using a number of different functions in the ensemble metadata class can be helpful. The one we often, at least Jess and I, and I think Matt and Emily have used the most is this closest lat long command. And what this will do is you specify a variable that's in the state vector, and you specify the coordinates of a proxy variable. And this command will search through the state vector and will locate the spatial point that is closest to those coordinates. It does this using a Habersign function, so you can use -180 to 180 longitudes, when you 0 to 360 longitudes, you can use a mix of both. It doesn't really matter. Trigonometry ends up the same. Let's see. Oh, and here I have a comment that when you're working off with a tripolar grid, as we are. Actually, let's do this a different way. Let's look back in that the grid file for the SSTs. You can remember that everything is organized down this site dimension. So by default, when you run the closest lat long command, that's just going to look for a latitude dimension and longitude dimension. And if it doesn't find one, it's going to be unhappy. However, if you have your things organized along the site dimension, then you can use the site flag and indicate that, like, hey, my latitudes are the first column of this site metadata, my longitudes are the second column of this metadata. And so that's kind of this slightly adjusted here. You're going to put in this site flag, and we put in columns, which should be a vector with 2 elements. The first element is the column that has the latitudes, and the second element is the column that has the longitudes. So I think maybe before we run this in the loop, it might just be interesting to see this for a single case. So let's load the metadata for the first proxy sites. So that would be site 1. Console. When we look at this metadata, we can see, okay, there's an ID that identifies the site, it's latitude, and there's a longitude. And if you forgot which one was latitude and longitude, you can go into this UK 37 grid file, see that the site metadata columns are ID by latitude. MATLAB has a function called str to double. It's a string to double. Double is MATLAB's kind of default number numeric data type. And if you look at this metadata, you'll see that I've written everything in strings here. So we're really quick going to convert these into numeric values that we can pass into the Habersign function. So we'll do like proxy coordinates, string to double. We're going to index into this site metadata. We want values 2 and 3. What did I do? Oh, I don't think. Sorry. For site 1, second and third metadata buckets. There we go. So there's our proxy coordinates. And let's go ahead and we're going to get the ensemble metadata object or that ensemble that we built. This is kind of those ensemble commands that we talked about earlier. So this metadata object, as I mentioned, is the thing that knows where everything is in the state vector. So it's the thing that's going to be running the closest lat long command. Next, we're going to ask it to find closest site. We do ans meta closest. We're searching in the sea surface temperature variable because that's what we need as inputs to the forward model. We're going to give it our proxy coordinates. We have that tripolar grid. We say that the latitudes and the longitudes are on the site dimension. They are columns 1 and 2. So what this is going to do is it's going to spit out the state vector row that corresponds to the model grid point that is closest to these coordinates. It's that row. Like, cool, great. This is a good time to do some sanity checking. So we can use the ensemble metadata object to query the metadata latitude and longitude at that row and make sure that it's pretty close to our proxy coordinates. So we're going to double check row. I think I showed earlier that metadata objects have that rows command. I'm going to give it. I actually don't remember the syntax. Let's do that. So it looks like I need to give it the name of the dimension that I want metadata for. And then if I want, I can give it a row. I can query a specific row. So we're going to ask for the latitude metadata at that row that we just calculated. Give it a console. Oh, sorry. It's the site dimension. My bad. Cool. And you can see this is the latitude longitude coordinate that is at that state vector row. We compare it to our proxy coordinates. We can see, yeah, no, these are pretty close. This really is the closest grid point that's in. So it's just kind of proof that this works. What we're actually going to do now is we're going to move some of this up into the loop. So, before we actually run our loop, we're going to need to create that metadata object. I'm going to cut this, paste it up above the loop. And then what we're going to do is within the loop, we're going to create a baseline model. But then we're going to locate closest site. So the row for that model is going to be, let's see, proxy coordinates. This is where we converted proxy coordinates from string to double. So we're going to get coordinates for the S proxy site. It was the second and third columns. We're going to use that to locate the closest row. It's meta in the SST variable, proxy coordinates, things are organized down the site dimension. And then finally, we're going to give this row to the forward model object using the rows command. Rows, here you go, there's the row. Once all that's done, we'll save the model setup.
That should be model. Oh, I see.
We're going to delete this stuff down here for the example. So, yeah, we go ahead and run all of this. It's going to think, hey, it's done. Clear the console. We look at our models, it's still a whole bunch of baseline objects. But now let's look at a specific model. Let's look at the very first one again. Again, we have to use curly braces to index because we're in the cell. We can see that now the rows have been set. So this forward model, it's ready to go. We can use it to estimate. There's a fair bit going on here. So people have questions on any of that?
For the proxy metadata, does it matter whether longitude and latitude? Or like which one comes first? Does it matter or?
For the proxy coordinates should be latitude, then longitude.
Okay, yeah, and we have to know that.
Yeah, and that is, if you read the help text, that's in there. Okay. Likewise, if you're using this site flag because you have tripolar data, then the first column should indicate, like, the metadata itself can have the coordinates in any order, but you need to specify the latitude column first and the longitude column second.
Okay.
I was wondering, so yeah, you specified the variable here and the site to give multiple times, your state vectors, or we are specifying that as well.
If you have multiple,
Times,
yes, this was kind of in the end trend example. What would happen then is you remember with end trend, we did a sequence of one of each month of the year. If I ran closest lat long there, I would end up with 12 years. 12 rows. One, corresponding to each month. It would be the row that corresponds to that closest spatial site in each of the 12 months. So then it's kind of up to you in this loop to be like, cool, I want the June ones, or I want June, July, and August, or I want all 12. It'll depend on the forward model and what the forward model is saying.
I guess you could probably do it through one thing, but you want to have stencil and sort of then.
I'm not sure what you mean by sense in space.
So you thought the other for it was averaging over.
Oh, yeah, you could use it to search. You probably wouldn't use the closest lat long because that is the closest one, but you could use the you could search along the rows to be like, what are the rows that have latitudes within this box and longitudes within this box? I would support we do maybe like a 5-minute break.
Yeah, sounds good. Is everyone following? What are we doing? Okay.
Just a quick question on that. So in end trend, right, we've got some that are like July sensitive, we've got some that are like April, September sensitive. So just looking at here, the way you've done it is you've got multiple regressions. If you wanted to just say, okay, I just want the average temperature from April to October, right? Would that mean in the ensemble you have to create April through October?
I would implement that as a mean rather than sequence, because if I'm always using the same like April through October mean, I could just do that in advance and up a much smaller state vector. So,
Right, but you still need to create, so you can't create that mean that would be in the proxy system, right? You have to like.
it depends on what your proxy system model does. Like it could, I don't know what it does. It's external to that.
I guess it's asking, like, in this case, a good example would be, for some regions, actually, the alkaline are seasonal, right? So let's say I wanted to be JJA instead of median, right? Like, can I take that average in this loop, or would I need to already have like a JJA in my ensemble?
Right.
Like, is there a function to kind of pre-average it before you send it to the PSM there?
So there's not a specific function. This is hard for me to answer because I feel like there are different approaches you could take to do this. One thing you could do is in your state vector, you could have the seasonality. You could have all the possible different seasonalities. And then when you create this forward model loop, you could, run some function that checks what the actual seasonality is, and then request data from the correct seasonality. Another thing you could do is determine the seasonalities in advance. And then you could, when you build your state vector, maybe you include a variable for each proxy record that just has data from the grid point with that specific seasonality.
But maybe it would be easier if you just save monthly in your state vector to be able to, if you have a lot of different combinations of seasonality to be able to just do that in this, because that's what I normally do all the
Yeah,
time.
if you look at the end trend demo, that's exactly what we do. That's why we have that T monthly variable, is when we get to this like proxy loop, then we can be like, hey, what are the seasons that matter? Okay, give me the rows, the climate model grid point in that T monthly variable. Now that I know it, and so that'll give you 12 rows, one for each month of the year, and you say, okay, now I'm gonna look at this proxy seasonality, it's April through October, so I'm just gonna ask for data from, these specific rows.
The way, but unless I'm wrong, the way this is happening now is it's going, okay. April times COVID plus. May times COVID plus.
Let's just pull this up.
Whereas what I want is the average of April through September. On a single coefficient plus.
Are you kind of on this like
Yeah.
whole demo loop
Yeah,
here? Okay, so. Right now it's implementing a seasonal mean.
Well, it's taking the slopes, so maybe I'm not getting it right.
Oh, yeah, if you look at the LGM demo in step 3. I kind of kept, what I did with Entrend in reality was I pulled out the season. I made a variable for each site and I put it in my state factor. And it only had data from that single grid point in the season that I wanted. That's more work to code, and so I didn't want to touch on it today. So I kind of did this simpler
But you wouldn't
approach.
do it, yeah.
You could though. So what's happening here is we're implementing a seasonal mean, and we just note that, okay, I'm taking, like, here are 4 months.
Yeah.
Well, divide them all by 4 and run that as a linear model. That's a linear average, if that makes sense.
But I
Sorry, I
guess
get
it-
excited.
I'm not sure where it's.
but
No, I do
there's
like.
no way to pull out an average, like, right, like going back to the baseline example, like. I can use baseline to check to see if I'm in the North Atlantic. In that case, I want a JJA instead. There's no way right now to build that into.
Yeah, there is.
There is. Okay, how?
So
Like assuming you have in there.
it would look something like this.
But is that? So you're finding the row and then, but these are different, these are vastly different.
So I get all of this and then I check to see
Oh,
base
okay.
and latitude and then I pre-name them. And then put
Okay.
them into these.
I think you could do it like this, Jess, where you're like, okay, the season for this particular proxy.
So you get all 12 rows and then pull out. this.
But
Okay, okay, I think I'm following. Yeah.
You get all the rows. You need to
And then
average
you-
outside of.
Yeah.
The linear line.
yes,
Before you put it into the PSM object, right? So if we save the monthly in our state vector, then we'll be able to. So when you get closest lat long from monthly,
you're talking about this end trend example.
well, I guess it's not a good example, since
In this end trend example, I have a single linear slope that I apply to a seasonal mean. But when I run this command, I get like 12 months,
in
and
the
then I pare
rows,
it
yeah,
down to the months that I care about.
that's, okay, that's.
And if
part.
there's 4 months for that one seasonal mean, I can take the slope divided by 4, it goes through the linear model, it would be doing essentially the mean of those 4 months.
Right, it's that part under locate data,
Like,
yeah, so that's how you.
What's I'm missing, the sun is not the same as the arcs. Anyway, this is something.
it's like, if I do June over 3 plus July over 3 plus August over 3. Right, that's the mean of June, July, and August.
Right, it's more the slopes that you're dividing by 3 and 4.
Oh, that's because I give the linear model 3 inputs, right? Data from June, data from July, data from August. I want to implement a mean, so I say, all right, the slope for June is whatever the slope for the mean is divided by 3. the slope for July is the slope of whatever the mean is divided by 3. Is that track?
Because the model we built says it's actually JJA times beta intercept y. G1 times beta divided by 3 plus y times beta divided by 3.
So. What I'm gonna use beta. Beta is the slope.
But you can tell me if this is, but at the moment, this is not how I would model a simple here.
Forget the intercept for now. Like, this is what we want.
Yes, that's what we do.
Okay, and so what this line is doing is I'm replicating that initial slope over the number of months. And I'm dividing by the number of months. So what I'm essentially doing is d over 3 June less d over 3 y. D over 3.
Yeah, what I'm saying though is that like that's not the same thing as beta times y.
Just like. I think it is. Just because like.
If I look like built is not. Anyway. I don't think that's the case, but
Okay.
If that's the data. When you get the slope, it depend on the data.
right, exactly.
Right. It's not just one numerical value, but the slope that you get is coming from the regressions of the data set itself, so. It's might not the same when we write out the.
Well, I'm just good. All right, let's keep moving, but we'll talk about this after.
Let's say that the anomaly for June and August is 0, and the anomaly for July is. You divide beta by 3. That's the same thing. Right? And the different months weigh into the average typically, and so that's going to change your. Yeah.
Wait, why would months weigh different?
Because I'm saying, okay, what's the total here, or what's the average here? I'm not confused, but maybe I'll do the math and stuff, but I don't think you can just divide the slope by 3.
This is what I.
It's like a model switch additive. I think actually
Seems weird to me, but okay.
The data is already predetermined.
Right,
All
you can
lines.
instrument the data.
It should be okay.
Yeah, Zeta was determined in bits.
Probably not how the way I would set it up.
No,
it's not
dated, but I think it should work. Mathematically, it's the same, but also, yeah, you don't have to set it up this way. I think in the expanded tutorial that we were writing earlier, there's a like slightly longer way to code the state vector that also is more efficient and avoids this. You know, do that. There we go.
Great, or are we going right now?
Let's be on break.
Guys, let's do it that way here.
Mostly, Kevin, this was to like try to keep the like external code
Sure.
to
Again.
Yeah.
And up to this party haven't calculated.
Not yet, yeah.
Just set up the.
This is setting up the PSMs and then when we come back, we'll actually run this line and we'll actually estimate the value. So That's like one
There's
line.
two concepts.
If
Like,
you're
let's
still
do
running
this,
your-
where's the,
What, your current model?
I was because, because I haven't updated this dashboard for. So yeah, I was running my outside, but now that they're pretty much, that was just because. It wasn't set up. So now we can run here.
yeah,
But
like
you
we
can run.
here, everything.
Yeah, that's like.
Which one is running out?
Yeah, you can just run.
Cause I'm showing errors on it.
You can.
Yeah, I mean, like I do. No,
This
it
one-
runs
yeah, I-
fine to do here.
Sometimes this needs really to like.
This one is, it doesn't know.
Sanity check. You know, make sure that everything is the right.
That's something I don't. Else is thinking here.
So ultimately, like, which one of them is video?
Yeah, I mean, it runs through the loop and then it's this line down here.
What's it in? Can you just print the fonts? That's on. Let's see. Okay, cool. I'm just running basically. From the groups.
Running on it. Sorry.
So this is the suggested.
Oh, okay, we're on it.
So what happens if you just give it some down C surface values, like is the forward, because this to me looks like the forward model is very fine.
Okay. Sorry, I didn't say it.
Yeah.
It's easier for you. Oh, I don't have a toolbox.
Yeah.
So just download this curve fitting toolbox. I should be good to go.
Yeah, I have one question for, I'm a little confused about this step in terms of like, my understanding of what we're doing this morning, we were sort of setting up. We're manipulating the entire like setups that we had. For the PSM. That was like two different, like, you can do it at different steps.
Kind of the way we're. There's different ways to approach the problem, right? The one way is like in this LGM demo. We're reconstructing the SST field, also using the SST field as the proxy input, so it's just like. This is our reconstruction already, but also like this value. It's not intuitive, but I can just go rating them once. So kind of speak to the rest of the people. It's not no, it's super fun. Yeah. I think it's it's like, hey, we want to reconstruct. Yeah, it's something like that. It's just standards. You could also toss in like SSTs or proxy one. SSTs at the small 2.2. Then like.
Yeah, I guess it's one of the case studies in it for very normal. Like that. Normally it would be ensemble.
I think that's really cool.
Don't hesitate to email.
Yeah. Gotta make my car.
Yes. That's love.
I don't think I would get that, but I
It's correct this.
It's nice meeting
All of you, I would say all of you.
Alright.
Goodbye individually, but.
It's amazing.
So we did.
Unders.
Oh, that's what I was trying to do, but that didn't.
Yeah, so now. Yeah, in this it's actually just about this. Yeah. So you. Hey, yeah, no problem. Here's okay. That is interested in this ensemble, the person toolbox. Did it say like every single PSM failed? Yeah. Yeah. I'll try downloading the current.
Around the street. Is that that you needed for putting?
Yeah, I didn't realize that. So yeah, people are getting a bunch of errors. Apparently, you need the curve, MATLAB's curve fitting toolbox to run baseline. So, yeah.
That is probably not my fault, it's actually not your fault, because I think baseline, the B-spline expansion probably is a
Oh.
function of the curve,
Okay.
if I had to guess. So that's, yeah.
Wait, so because I can add like PSM dependencies. We can have her fitting toolbox will stay in there, but I can also it's changed.
Likely on my latest versions, I think we can, yeah, like since something you should be able to set up.
So use, yeah, I think these functions, not like ST mock or.
I think they're added.
Yeah.
Okay,
For anyone on Zoom,
yeah, so that's.
oh, okay, it's like just reply, but if you're getting every single proxy on screen, you may need to.
Yeah.
Which,
No, I think it's.
Oh, okay, cool.
So that's my bad. I should write.
Okay. Okay. Yeah. Sure, yeah.
First it runs on my site.
Yeah. I just. Wait, what's on it? Oh, I figured you gave us.
Yeah.
Yes, if you go to add-ons. Yeah, in that lab, so you're on your phone, there's this like add-ons, click on that and then.
Cool.
Oh, very much.
Yeah, so this is a requirement of baseline, not a requirement of.
As far as I'm aware, Dash itself doesn't require a toolbox, so this is kind of.
Yeah.
Maybe a statistics toolbox, but I don't. Cool. I think that's kind of like.
You got it.
Sorry. It wouldn't be better if I call it spline toolbox or something.
Or it's fine.
Yeah, spline high. Spline. I haven't translated this one yet, so I haven't got that exception.
So cubic splines are in the stats model.
I'm sure there is a way,
Library.
it's a pretty basic spline function. If there's cubic spline, then. These splines are like the lowest level splines. I think that's okay.
Like either it tries to download every toolbox and or you get like nothing.
We natively. That was so.
What is it?
Yeah, you're still running a zero, but instead of like now that's not fully native. On this new Apples and just.
Oh, really?
Yeah. There's a couple toolboxes they have to be.
I guess it's
I mean, nothing.
nothing major, no. That, I just, yeah, I would, still getting errors, something else, so Claire's asking.
Yeah.
I have this.
Where visually is baseline on your path.
I think they are.
If you type in
like the.
here,
What's the guy?
you can give you some code and I say, yeah.
Yeah. I don't think I would use.
It broke on me.
If you type in that code onto
Oh, yeah. That's good. Yeah. Because he has how it is. Seriously? Yeah.
That's weird.
You can pirate it.
Yeah, what are you pirating?
Well, so Edcard's not allowing Joe to download the current Toolbox. They're putting a lock on it, so it's just bizarre to me.
Okay. It looks like maybe people also require the statistics and machine learning toolbox. It sounds like maybe most of the people here in the room already have that downloaded, because I think this is running for people for the most part.
Yeah, I have that one already.
Yeah, I think that's one of the worst things.
I just run that.
Did it?
Yeah.
It
Sounds like something
You could just.
I wonder if.
Oh,
I bet if you're.
It's, I use this one to Norm Rand.
Yeah.
He's in the statistics and machine learning tool.
Yeah, I think Claire was having that happen also. I think there's two toolboxes then. It would be the curve fitting one is in there and the statistics toolbox is there. And probably anyone who downloaded like the free trial license yesterday, it probably gave you nothing beyond the bare stones, so.
Well, I usually check any boxes.
Oh, okay. Yeah.
Yeah.
I think Norm Rand is actually in that toolbox, but I could, Rand N probably is, right?
I mean, Dash definitely has like eight as a requirement, which is part of statistics, so I think.
They can close it. Actually, download it.
I can just change over Rand N, download the site toolbox, so I'm not gonna do that. I will do that. in this
So right, Norman is his stats where it's
I'm
toolbox,
sorry.
where random is just in the core.
Okay, okay.
That's good. That's ways.
That's really, yeah, that's really
Yeah, I didn't have a problem with. Yes, everybody. I heard about the UK and Stockholm.
Exactly.
Okay, so that sounds like you're having one of these that everyone else is, does it, what is it?
It's just doesn't.
You need to-
Oh, so that might not be on your path then,
Oh, okay.
so
So just send the path.
did you download the baseline?
All right, lesson learned.
It's not.
I always have those toolboxes installed.
Oh,
so
there's the
I didn't
PSM.
know. Yeah.
Alright, because right now the code's not on.
Yeah.
Yeah, I have no idea what the functions I use, where they're coming from.
Especially Norm Rand, that one surprises me. And the other ones is like,
I know,
okay,
it's so
that's
basic, right?
fine, but.
Also, you have to do.
Right, not every time, it's the one time to get it on your computer,
But if we close MATLAB,
it's still gonna be.
okay.
All right, maybe we can reconvene. Is everyone toolbox up and ready? Good-ish. Cool. There's really not much left to the whole PSM part of this. The final command here is we're going to generate our estimates. This is the output of PSM.estimate. This takes 2 inputs. I never remember the order of them, so let's look that up. It is the models as the first input and then the ensemble as the second input. For the ensemble, you can use that like X data matrix that we loaded earlier, but you can also use the ensemble object, either one's fine. So models, and here's that ensemble I created. Let's see if I get it right. It at least works on mine. So it's thinking, and it's done. So you can see over here in our workspace, we have this YE matrix. It has 89 rows. That's 1 for each proxy record in the network. It has 16 columns. That's 1 for each ensemble. So they all failed to run. It's basically like that. Yeah, try to. You might. Did you get the statistics to it? Do like UK forward. Yeah, and so that's it for the PSM interface. Does anyone have any questions on that? I kind of took a break right before the very end there, and I realized we had Toolbox stuff. Right? Cool. Well, with that, we're kind of in our final hour, and so let's jump into running the Kalman filter. And I have good news, which is like compared to everything else, this is probably one of the easiest steps. Yeah.
So presumably, because you're not spinning out the like PSM ensemble, you're just spinning out the prior ensemble. So is your R in these scripts?
Oh yeah, so I should mention. One of the things about baseline is that it can estimate R values for you. Some of the PSMs in Dash that are supported by Dash can do this, some can't. You can use that psm.info command. You can see who can estimate R up here on the far side. But right now you can see it's the Baywatch PSMs. Those are the ones that estimate. So when you run psm.estimate, you can ask for R as a second output. And whenever a PSM is able to estimate R, it will be in that output array. If you include models like the linear model, that's still fine. It's just going to return a NaN value for R if it doesn't have the capability to estimate that. So
Also, the R that comes out of that is going to be, well, I guess you're going to do it.
yeah.
Yeah.
So I was going to go ahead and run this command here. And so there goes the estimate, it's thinking. We're going to get some outputs. We look at our workspace, we see we now have this R output. And if you'll notice from baseline, this one's going to have the same size as the proxy estimates. That is to say, it has 1 uncertainty estimate per ensemble member. Now, in actuality, for our Kalman filter, we only want 1 set of error estimates. And so we're just going to take the mean of these uncertainty values across the ensemble. So R is equal to the mean of R across the columns. 2 is the second dimension, so we're taking for columns. And when we do this, you can see here's this column is our vector of proxy forward model uncertainties. And these specifically are error variances, which we kind of talked about this morning as kind of the common way we do things, but yeah, we can also think about error covariances as we move forward.
Yeah, and you notice that these are really similar values, so you could also just
use point.
manually set R later.
If you got everything to run, maybe go ahead and save YE and R, because if you're me, you're very likely to clear your workspace at some point, and this will just have them for for when we run the Kalman filter later. So I'm just gonna say proxy estimates. I'm gonna save the YE variable in my workspace, save the R variable. That first input is just the name file I'm saving. You see over here is now this proxy estimates, which I can load later if I need to. Later,
Sorry, you answered it right when I was about this.
Okay.
I have not used MATLAB.
oh, yeah.
So R doesn't have to be a matrix, right?
Nope, R can be a vector, but it can be a matrix. We'll support either way. And then ultimately, if you give dash a vector of R's, it's going to interpret them as error variances, and it will just turn it into a diagonal matrix when it actually runs the equation. Okay, so we're on to the Kalman filter. We're actually gonna run our assimilation. Swap out a microphone. So before we jump in, I'm just gonna give a real quick brief comments about the algorithms in Dash. And we'll kind of look at some of the features of the Kalman filter class, and then we will run the simulation. So within Dash, we have three main data assimilation algorithms: the Kalman filter, particle filter, the optimal center. Yeah, and each of these classes is going to make an object that's going to let you run, one of these types of analyses. And the main thing I just wanted to highlight here is that each of these algorithms are like completely independent of the rest of the toolbox. You don't have to use grid file, you don't have to use state vector, you don't have to use PSMs. Those things are strictly for your convenience. So if something's not working for you, you're free to work on the data matrices just on your own in MATLAB as well. Got a little description of the different algorithms here, but I think for the purposes of time, we'll just jump forward and look at the Kalman filter. So the way that Kalman filter class is organized is you're going to create a Kalman filter object, and then there's going to be a few things you can do with it. The first thing that you always need to do is you need to provide the 4 essential data inputs needed to run the filter. So this is going to be the prior. These are going to be the proxy records, the proxy estimates, and the proxy uncertainties. So we've seen all of these now over the day. We made our state vector to make the prior. We have the proxy records in that grid catalog. And right now, we just generated proxy estimates and uncertainties. So to provide these inputs to the Kalman filter, there's a command for each of them: prior, observations, estimates, and uncertainties. Yeah, use the one that corresponds to each of them. Kind of one of the features of our Kalman filter class is we support a number of different covariance adjustments. I think we touched on a number of these throughout the workshop, but for example, we can implement covariance inflation, which multiplies Kalman filter covariances by some scalar value to increase the magnitude of your updates. There's localization, which we talked about as a way to restrict the influence of proxies within a specific geographical region. And there's some other things that maybe we didn't touch on so much in the workshop. There's this idea of blending, where you can combine a covariance for a very small ensemble with the covariance from a larger ensemble. And in some cases, you may just want to provide covariances directly to the Kalman filter. I think this comes up the most when continental configurations change, and it can be hard to define, if I'm looking across a changing continent, what is actually the covariance here? Is it stationary? Should I come up with something? So yeah, the set covariance command will let you to just set something directly if you need to calculate those covariances offline at your own. The other thing the Kalman filter class does is it gives you some options on what the algorithm is actually going to output. So one thing we'll note is that that's probably fine. We use an ensemble square root Kalman filter, which is kind of the standard thing that I think most of us are using for Kalman filters. And a key distinction here is that it updates the ensemble mean separately from the ensemble deviations. So the ensemble mean is, we saw in the last discussion yesterday, hotly debated, I don't think it's hotly debated, but it's often what we'll use as like the reconstruction itself. And the ensemble deviations, they tell us about the spread and the uncertainty in that final reconstruction. Now the ensemble deviations are much, much larger than the ensemble mean. And so it's a lot more computationally expensive to update them. So by default, Dash will only update the ensemble mean. And this can be nice if you're running a million frozen proxy network experiments, or you want to try out 500 different localization parameters or such things. Because it can be several orders of magnitude faster to only update the ensemble mean. That said, the deviations are really important for uncertainty quantification. And so we got a couple commands to help you provide those. The first one is just this Kalman filter.deviations command, which will return the full set of ensemble deviations. The issue here is that for very large state vectors or simulations with many time steps, this can just completely overwhelm your computer's memory. And so you might need to take a slightly reduced approach. So some other options here are to return the variance of the posterior or to return some specific percentiles. And then once you've kind of made your selections, done any covariance adjustments, you've asked for whatever outputs you want, you can use this run command to run the output. So, does anybody have any questions off that? Cool. So just jumping right on in then, we're going to start by using the Kalman filter command to create a Kalman filter object. As usual, kind of in Dash, you can, when you're creating one of these objects, you can use the first input to apply a label if you want. So I'm going to create Kalman filter. I'm going to call this KF. It's just how I like to write things. This is our LGM. So when we create this object, you can see, okay, here's our filter. Doesn't have observations yet, doesn't have a prior, estimates or uncertainties. And right now it's just going to return the ensemble mean. So our next task then is we're going to provide those 4 essential inputs. And so as a reminder, that's these things here, the observations, prior, the estimates, and the uncertainties. We can look in our workspace and we have our ensemble, that's our prior. We have our uncertainties, that's R. We have our proxy estimates, that was YE, that we just pulled out of the PSMs. The last thing we need are the proxy estimate, the proxy records, which are in that UK37 data file. So let's just load those real quick. E is equal to grid file UK37 dot load. And we can just write in the other ones here so we remember what they are. X is the ensemble. Just going to put a comment here that YE, or sorry, I'm sorry, this should say Y. These are the proxy records. YE is from PSM.estimate. Likewise, R is from PSM. So we can use those 4 commands to provide changes to collect. Oops. Now we'll provide
It would be useful if we just write the code to load file. Oh, maybe it would be useful to write the code and load file, load department file. As if you didn't have enough.
You're talking about YE and R? Yeah,
Yeah,
let's do that.
And the ensemble too, just because
Yeah.
often you might do step later or something.
Okay. What would we call this? So proxy. Save.
Proxy estimates.
Yeah. Let's load. We're going to load this from that proxy estimates file.
You can just load it and it'll automatically
Yeah, but I don't like it from a coding standpoint because you don't know what's happening. So then what I
No,
would
but
do,
you can specify what variables. to put.
but then it's still a struct. But okay, yeah.
You can just say YE
YE and
or
No,
No,
yeah,
okay.
load proxy estimates, YE are, right?
yeah.
Yeah, but this is still a struct that has YE and R in it.
No, but if you just get rid of the output,
Oh, you want to just load it directly? Yeah, okay.
yeah, and then.
Yeah, okay. Yeah, so we'll load YE and R.
And then you need to load the ensemble.
So the ensemble, you don't need a load. You can always use an ensemble object to stand in for the ensemble in Dash.
But we don't, let's just clear your workspace there.
Okay,
So,
yeah.
Then you need to at least sign up.
So this
Yeah,
is
I
the
guess that's fine, not loaded.
Yeah, no, that's a good point. This is our LGM ensemble. I'm gonna touch really quickly. There's a command called ensemble.useVariable. It's not gonna come up in this LGM experiment because if we look at our ensemble, we can see there's only a single variable here, the SST variable. But if you have multiple variables in your state vector, you only need to give the reconstruction targets to the Kalman filter. You don't need any of the forward model inputs because we already used them to make the proxy estimates. So you can use that use variable command so that the ensemble object will only represent, a specific set of state vector variables. We'll even do a little aside here. Let's pop into the N-trend demo real quick. Into ensemble is equal. We're gonna create the ensemble object for the ensemble we made. You can see our ensemble represents, those three variables. But the T monthly variable, that was strictly for running forward models. So we don't actually need to use it for our simulation. And so you can use use variables. And the input is just the names of the variables that you want to pass to the Kalman filter. So I would do like JJA variable and the temperature index. And now if you look at this ensemble object, the data in the file hasn't changed at all. But when you use this object to do things, it's only going to load the values for these two variables here. And so that's all that will be passed to the Kalman. Any questions on that? Okay, so I'm going to clear everything again. We're going to go back to the LGM. I'll go ahead and load everything. And now we use those 4 commands to pass these inputs to the filter. So Kalman filter observations. Those were our proxy records, Y. Give it our prior. It's X. We're going to give it the estimates and the uncertainties. So now if you do this, let's look at our Kalman filter object. And we can see, oh, hey, there's a lot going on here now. See, it has observations. It's going to use a static or stationary prior. It has estimates, and it has uncertainties, and it's specifically using our variances, opposed to covariances. It also knows like the size of our assimilation, state vector, number of ensemble members, proxy sites, etc. At this point, it's going to return the ensemble mean. So at this point, we can start thinking about applying some covariance adjustments. What are we doing on time? People want to talk about localization? Raise your hand if you think you've used localization. Okay. All right, let's just run the simulation once and then we'll look at localization after that and run it again. The next thing we can do is we can just run this. Run filter. The command is onFilter.run. Doesn't take any inputs in most cases. Yeah, you're not gonna, if you're worrying about inputs, there's something else is going on. So, it's gonna create an output structure as the single outputs. So if I do this, right now I'm returning the ensemble, the updated ensemble mean. So when I run the filter, boom, it's done. We updated, we run the assimilation for the last glacial maximum. We're gonna have this variable a mean, that's a stood for analysis, just sometimes what people call the posterior. But yeah, we're looking at the updated mean here. We can see it has this, it's this state vector over this one assimilated time step. We also return the calibration ratio. I don't think this came up much in the workshop, but this is sometimes kind of a tuning or assessment parameter that people are interested in. Now, this is great. It's really fast to run, but we don't have any uncertainty quantification for this. So let's run the Kalman filter again. This time we're going to return the full set of deviations. And I'm actually going to, let's time this real quick. Let's time this once with the ensemble mean and once without. The tick and talk functions are how MATLAB like sets a timer and then stops a timer. So what this is going to do is just display the time that it took to run the algorithm and update the ensemble mean. I'll say just, so I'll call that. So it takes like, I don't know, a little under half a second. Cool. If I clear my console. Now let's have it so that the algorithm will also return the full deviations, the full ensemble posterior. Here we're going to use the deviations command, and we're just going to set it to true, saying we want the deviations. So if we do this, we can see now, okay, yeah, this Kalman filter is going to return the mean and also the deviation. Now let's run the filter again, and we're going to time it. So if we rerun this filter and time it, see, okay, yeah, it took a little longer to update deviations. If you're working with the end trend example, this difference in time is like much more drastic. Like it's maybe 100 times, 500 times faster to run just with the ensemble mean. So certainly play around with that, particularly if you're doing optimizations with really large state vectors. It can be pretty nice to not update the deviations.
Yeah, it scales with how many ensemble members you have. So in this case, we only have 16. So
It's a pretty small ensemble.
it's pretty small, and other dimensions too. So.
But if we look at this output, now there's also this field A, D, or dev for deviations. And that's, you can see the whole posterior here, state vector, overall 16 ensemble members. If you look in the documentation of the Kalman filter class, you can see what the names of the different output fields will be. If you want to return the variance across the posterior ensemble, you can do variance and set it to true. And this will create an output called a bar. Now we're returning mean, deviation, variance. We run the filter. You can see the output has this a bar field. And this can be nice if you have a really big ensemble or a bunch of time steps. This a deviations field can just be way too big. Like it can be like a couple terabytes in pretty quickly. Whereas this, you see this variance field, it only has a single state vector in there. So it's much smaller, much more manageable.
And just as a note, the true full posterior is a mean plus data.
Yeah.
So we didn't really talk about this, but the way that the Kalman filter is solved, you actually split out the solution for the mean deviations. And so that's why they're estimated slightly separately. But you have to add them. If you want to look at the full ensemble, like what Julian was talking about yesterday, you have to add them back together.
So I'll go ahead and even add a line in here for people. Should be like rebuild for posterior. And that would be A, the analysis is the mean plus the deviations. So that should be this. Yeah,
And MATLAB is smart enough to add. Essentially like, to add those together.
it's probably we used to call it binary single expansion, which is a terrible name. What is it in Python? I think it's called broadcasting. That rings a bell with anyone. But modern versions of MATLAB will now broadcast, and the old ones didn't, but the old ones can't run Dash anyways. Yeah. So from here, you're kind of free to do whatever you like. You know, you might take this ensemble mean and reshape it into back into a spatial field. You can map that up, visualize it. You know, you can play around with like how do these uncertainties go over time. You can also return. I didn't mention it, but you can return like specific percentiles. This is also on the workshop website, but you can use the percentiles command. Maybe I want to return the quartiles of the ensemble. So values at 25, 50, 75%. If I were to do this, the outputs would have this A per field, which is, you know, at the posteriors percentiles at the three requested percent.
So down under the open coding 5, on the visualization tab, see if you want how you can reshape. You can easily just sort of reshape the posterior back into a grid, then plot out. I mean, it's gonna be tripolar still in the case of SFT, but
Yeah, so there's this ensemble metadata.regrid command, and this command usually comes into play after you run the Kalman filter. But the way it works is you can give it a data array that has at least one dimension that's the length of the state vector. And you can say, hey, I want you to go into that array and I want you to pull out a specific variable and I want you to reshape it back to its original data grid. That's usually pretty useful for mapping. For this LGM demo, it's not going to do a lot because we only have a single variable in here anyways, so we don't let you extract one variable from the others. And it's on this tripolar grid, which is kind of hard in this long vector. But if we can jump over to ntrend really quickly. Let's just load our prior ensemble from ntrend just directly. Ensemble. It's pretty big. I'm going to clear my workspace except for that ensemble. You can see it's got this real long state vector. It's got a bunch of ensemble members, over 1,000. And it's also got these 3 different variables in it. But one thing we could do is we could pull out one of these variables and regrid it. So like, for example, what if we wanted to pull out this T monthly variable? So we could do that. We'd be like T is equal to metadata objects. It's regrid command. We're going to say, okay, I want you to pull out the T monthly variable from this prior. If you do that, see we have this T monthly array, which is some 4D single. Let's look at the size of it. We can see it's the 144 longitude points, the 30 latitude points in the northern hemisphere that we used, the 12 months of the year that we used in the sequence, and then the 1156 time points. When you use the regrid command, you can also return metadata as a second output. So we can modify this command. We'd be like, hey, I'd like the metadata, and this will be the metadata specifically for that regridded T monthly variable. So we can do that, and if we look at metadata, you can see like, oh, okay. You know, these are what the dimensions are that correspond to these sizes. And for example, we could look at metadata.time, and we're looking at the months that were in our sequence. We could look at metadata.lat, and remember like, oh, that's right, we were using the extratropical northern hemisphere. This doesn't go past 35 months. Yeah. Any questions on that? Cool. Well, that's a lot of coding. I feel like we could probably wrap things up here. Is there anything like anyone would like to see, or
I want to see a visual of the posterior.
visual of the posterior? Well, Matt,
We've done all this.
you sent me this lovely photo this morning, which I wasn't able to add to the website, but absolutely we should look at it. Thank you so much for making this too.
You're gonna just pull.
Oh wait, no, I downloaded it. That's right, that's right.
It's not really what I meant, but
The mapping toolbox and MATLAB can plot, tripolar grids, by the way.
Yeah, which is really nice.
There you go.
Yeah, ultimately visualization is kind of outside of Dash, so pull in whatever coding tools you like. Let's look at Matt's coding. What?
Code for there.
Matt,
Oh, you need the mapping toolbox.
you need the mapping toolbox.
yeah.
You don't have to.
This is not-
Matt's code is using the mapping toolbox. I use one that's called Map, which you don't have to download from MATLAB. That one's freely available as long as you have paid for MATLAB. So that's another alternative. The mapping toolbox is probably a little more powerful overall. You did some cool stuff like computing, changing continental coastlines.
Yeah, I was about to ask that, like the paleo coastline, was that like already in MATLAB? Or do you have to, that was like that.
Matt had to do that on his own, but like, yeah, takes the code, plot it up. Matt, do you want to tell us anything there?
No.
I thought I thought the coastline was really cool. I was very jealous because I've never had that. Yeah. But yeah, yeah, so we go back and this is that posterior that we assimilated.
You can also write this to NetCDF out of MATLAB if you'd rather use another plotting software.
Yeah, and it's probably a good thing to do anyways. Because MATLAB's proprietary, if you're gonna publish your results, like put it in a NetCDF and
Jonathan, if I wanted to, so X is now some ensemble, right? That has the priors in it. If I wanted to do a quick sort of like prior versus posterior, I use the ents meta.
you can use the regrid function on anything that has a dimension, the length, and the state vector. So let's pretend, like I'm gonna take this X variable and I'm gonna pretend that I updated it and I have the ensemble mean, right? Which would have this size. It would only have a single column because it's the ensemble mean. I can still do meta, regrid. Again, maybe this time I want the index, the temperature index from that mean. Let's get the metadata too. We should always have metadata. And there we would load up this index for the ensemble mean. It's just a single value. Look at the metadata, just like it's a single value. That was maybe a bad example. Let's do the monthly fields. So here we can see we have that monthly field as before, but now it doesn't have the 1156 time points because that wasn't part of it. And the metadata is there's allowance, there's a last, there's a.
So you can play with any of those types of plots.
Yeah, great. Now let's, if we want to take this one step further, let's say we have like the ensemble mean over a bunch of different time steps, maybe like 1,000 time steps. So we'll say like, heck, we're just pretending, but I'm gonna take this mean and I'm gonna replicate it over 1,000 columns to pretend that I have some like time changing ensemble. When I regrid this, you can see that this tmon variable, it's going to have longitude by latitude by our time sequence by 1,000 simulation time points. If you look at the metadata though, metadata doesn't know anything about these simulation time points. So your metadata is going to reflect the regridded state vector dimension. Your other dimensions are up to you. Like, do you want to? How do you want to call that? Like, it's whatever you find useful.
Yeah, I was just thinking, going through this, I have a question about, we just did the simulation, were we simulating all of the proxies, or were we like withholding some of them? Like, is there any ways?
We just threw in everything.
Okay,
Here.
got it.
But if you want to withhold them, we could go back to that code here. We could say,
Can you specify which
Yeah.
one you want to? Oh.
we could do like,
Yeah, not.
yeah, so we could,
That's-
okay, great. Yeah, so we could be like, I want proxies 1 through 5 for this one. Or I want proxies 1 through 8
you could
and
just-
also 17 and 44,
Okay,
and 1,005.
yeah,
But you also need to then put that into your YE and your R. So
Yeah.
you're-
So the way I would do this would be like use equals 8, 17, 4, oops, that's 8. Okay. And then I would be like proxies, use these ones. Okay, and then I would use use these ones. Are
nice.
So if you were doing like a leave one out experiment or something, you'd probably end up looping through the
Yeah.
options
Yeah.
and stuff. So you'd end up doing a loop group of the simulations, and what you can do then is, maybe just save a mean, or you could even say just one variable from the a mean to keep it faster and save it into a matrix.
Yeah.
For valid. I guess if you're checking validation, the other thing
oh
that is a little annoying is you do need to actually include all the variables that you need for the PSMs if you're doing cluster validation.
I have something I should mention too about validation, which is that you can use the psm.estimate command and you can run it on the output posterior and you can get validation proxies from it. Like you still have those forward models, but all the data inputs are still at the same rows in the state vector, so you can calculate those out and compare them afterwards. Yeah, it doesn't have to be a prior ensemble, it just needs to be an ensemble.
You haven't done both, like,
We haven't done,
okay, right.
do you want to, or?
I mean, I just thought that we might have done and I missed it.
No, it's very much there on the website. I mean, we can do a brief tour of it. I think the important thing to know about localization is calculating the localization weights is separate from the Kalman filter objects. And if I did it this way so that if you want to like modify the localization weights in a way that we're not currently supporting, like you can still do that before adding it to the filter. I know something that's been mentioned is like, we'll often do localization by just drawing a circle. But like maybe you could use like a climate correlation pattern to come up with a better like localization shape. So that's why things are calculated separate here. If you look, there is this dash.localize package. It's part of the toolbox. This contains any functions that you can use to calculate localization weights. Right now, we only support the Gaspari cone fifth order polynomial. But if you have a new localization idea, please let me know and I will add it into this library. So the way you would do this is you would do dash.localize.Gaspari cone 2D. And it's going to take the coordinates of your state vector sites It's going to take in the coordinates of the proxy sites. And it's going to take in, this is not a proxy uncertainty, this is the localization radius. And then it's going to make some localization weights. One of the commands for the ensemble metadata objects is lat long, which will just return. Yeah, we're just resuming experience. So we can get state vector coordinates using this lat long command. By default, it'll search along latitude, longitude points in an ensemble. So let's do trend. I'm actually going to get the metadata object for the entrance one. And I could ask for all the latitude, longitude points by the ons meta lat long. If I do this, we get this big variable over here. This is the coordinate of each element in the state vector. See, there's all the coordinates. Here's all the stuff that here's another pole. So that's at the bottom of the state vector. Here's a little more northward as we move up through the state vector and so on. Anywhere you have a big spatial mean, it's just going to come back with man coordinates, and so it's not going to be localization. So for that. The other thing we have is our proxy coordinates, which were in that grid file for the proxy metadata. So we'll do it like this. We'll say that the site metadata for each entrant proxy site. This. And then if you remember, we had that string to double command that turns a MATLAB string into a numeric value. So that's what I'm going to call it here. Here we'll look at the site. Good. Look at the site metadata. Remember, it's like the ID, latitude, the longitude, and the optimal growing season. So I'm just going to pull out the latitudes and the longitudes. Okay. We do that, we can see all of our proxy coordinates. We see the proxy coordinates are using a 180 coordinate longitude. If we look back at our state vector coordinates, we can see they're on 160 longitude. This is perfectly fine. It's not a problem. I think I mentioned we use a Habersign function to kind of calculate the distances, which is like constant. The last thing we're going to do is we're going to calculate weights. Do it with a radius of 22,000 kilometers. The radius is kilometers. And so there's a pair of weights that go in the column numerator. That's this first output. There's a set of weights that go in the column denominator. That's the second output. You probably don't need to know too much about what these look like if you're just planning on like testing out different radii, but you know, if you're going to develop a new method, I'll get in touch. Happy to talk more about it. But so dash.localize, we use that GC2D function to our state vector coordinates, proxy coordinates, our radius. So that gives us these big weight matrices, which are, you know, they have one row per state vector element, column proxy. And then when you have a Kalman filter, you can do a Kalman filter. You can provide these weights to the Kalman filter object, and it will apply them when it's the algorithm. So you get a Kalman filter, filter.localize, yeah. I'm not going to rebuild the whole entrant here, but if you go to the website, you can see what happened in that demo. Let's go to the demo. Yeah, it'll when you look at the object in the console, it'll show you that like, hey, I'm applying covariance. So that is localization. yeah, and like I said, there's inflation, blending, etc. Covariance. All these functions are pretty well documented. Check them out. I think I put some next steps. Yeah. So yeah, thanks for attending. If you want, try doing any of these things, like kind of alter the code from the demo a little bit. Good ways to practice things. I would say either next week or like early the following week, we'll probably push the official version 4 release. So probably include a few of these notes that people made today. And I'm also going to try to include like an expanded version of this workshop. So we'll have more on the grid files, a little bit on particle filters in there. If you're interested in learning about those. But most of all, read the reference guide. That's ultimately where all the commands are. Read the help for the different classes. This is a good order. I think we've all seen a lot of these now. So, and yeah, don't hesitate to reach out. Definitely, like, want this to be useful for people. So, please. Yeah.
Really package. See, kudos to you. Is
Thank you, everybody, for staying. I hope this now opens a whole new world for you as to something to implement your own MTA on. I can tell you it's way better than trying to do everything. So. Yeah, feel free to stay and play around with it if you like, or if your brain is done, you can take off, it's also fine, whatever you feel like, whatever you feel like, I'll probably just stop the Zoom at this point and stop the recording.